Hey YouTube! If you've looked inside any modern computer hardware, you've probably seen heat pipes. They are copper pipes which go from the processor to the heatsink, which is in another location. Heat pipes have a very high thermal conductivity, allowing the cooling action of the fins at one end to cool the processor, which is at the other. Hanging behind me, I have my homemade heat pipe. It's filled with water and water vapor at a low pressure. At the top and bottom end, I have a thermocouple whose reading is displayed behind me, and at the bottom end, I have a small dish of water which will help get the heat pipe in better thermal contact with the hot plate. A heat pipe is a thermal transfer device that works by boiling a working liquid at one end and condensing it at the other. The cool condensate liquid flows back to the hot end by gravity or by capillary action. The energy used to boil the liquid is given up at the cool end, conducting the heat up to 500 times more effectively than copper. After placing the heat pipe on the hot plate, the water inside begins to boil. The boiling begins at much lower than 100 degrees Celsius because there is a strong vacuum inside the tube. Once all the water in the lower end has begun to boil, steam travels up the pipe, heating the remainder of its length evenly, as seen in the thermal camera. After a short period of time, the temperature at the upper and lower end converges and stays very close as heat enters at the bottom of the tube. The graph shows that there is a lag between when the lower and upper ends begin to warm. In this time, the water inside the tube is heating up but has not yet begun to boil. Once the boiling begins, the temperature of the lower end drops slightly as energy is used to transition the liquid water into steam. The temperature of the upper end begins to rise sharply, approaching the temperature of the lower end as hot steam begins to condense. Once the heat pipe was up to temperature, I cooled the upper end using trifluoroethane. This drop in temperature allows significantly more water to condense and flow back down to the hot end. After about 50 seconds, the temperature of the hot end drops by 10 degrees, even while remaining on the hot plate. After removing the hot plate, I cool the upper end further and both ends of the heat pipe quickly approach room temperature. Opening the valve and emptying the tube shows that very little liquid is needed in order for the heat pipe to function. Too little water and the heat pipe will be saturated, with no liquid water to take up the heat. Too much water and it will fail to boil, preventing heat from being transferred. Now that the pipe is empty, I place it back on the hot plate and observe the temperature rising rapidly at the lower end, but only slightly at the upper end. Over 2.5 minutes, the lower end is heated by over 20 degrees, but the upper end is heated by less than 10. The same low conductivity is observed when cooling the upper end of the pipe. There is a drop of more than 10 degrees at the upper end, but less than 5 degrees at the lower end. Looking at the thermal camera, there is a very large temperature gradient that can be seen across the length of the pipe. The graph shows that once heat was applied to the lower end of the empty tube, the temperature gradient was never less than 5 degrees, and at one point was greater than 20. In contrast, once the heat pipe was boiling, the temperature gradient from top to bottom was never more than 5 degrees. I hope you found this video interesting, and if you'd like to see more like this, check out my channel. Thanks for watching.